Okay, so welcome to today's lecture. Um, it's a series of lecture totally. We will have 6 hours together in the lecture, but then of course you have the lab connecting too. So before most of you join me now, I have already told the students that came earlier about the connection of the lectures to the lab. But the title of today's and Monday's discussion will be simulation-based optimization for production and logistic systems. And then we are more looking at the optimization, simulation-based optimization from a user perspective. So this is not a computer science course yet. So if you register for my course in October, I think that one will be more computer science based. We're going to open the hook. Both we are going to look down into the engine of the simulation, but also into the optimization engine. I will give you some mathematics and also quite much about the computing part. But for this course, it's mainly about the relationship between optimization and production logistics system. I think many of you have already seen my name when I made course introduction. So my name is Emerson, full-time professor in Skövde University, but visiting professor in Uppsala University. So my title is connecting to automation, optimization, and simulations. And if you want to reach me, then please, usually it's more easier to reach me by email. Then this is the right email address. So if you see here, it's not very difficult. I think it's the same as other lectures, but you just put my name before that. Now, an overview about the coming today and also next week. So as mentioned, we have 6 hours lecture together covering this topic. So today, I think we will pretty much go through the first three parts. I know that if you have done your undergraduate in no matter it's Uppsala or other university or even in foreign countries, so definitely you have gone through some optimization lectures, exercises, and so on. And many of you would probably have done some linear programming. So for this course, I will just make sure that we come with the same background. So if you come with a different background, when we talk about optimization process and the formulation, maybe it will be a little bit different. So my job here is to give you all some terminology so that in the coming week, so it's more easier for us to understand each other. And before we start with some real optimization, don't forget that sometimes you shouldn't always use optimization. So in many cases, maybe you should just use something called design experiment. And design of experiments is something that's supported by many simulation software, including FACS. But then if you have a larger number of variables, so variables will be something we're going to define, then you have something more handy called a meta-heuristic optimization method. I need to keep emphasize that the meta-heuristics and simulation-based optimization, you will learn that from this course that yes, it seems to be very flexible and also powerful. But remember, it doesn't belong to the optimization method that is classified as something fast. So there is no guarantee that you will get your solution fast. But the even worse is you cannot get something called a mathematical optimal, or you even can't simply call the solution you get from meta-heuristic, call them optimal. In papers, we usually write near optimal or close to optimal. That was the reason compared to other mathematical optimization that you have done before. So, and then even though we will start some simulation-based optimization today, but this topic, multi-objective optimization, most likely we will leave it to Monday. So we will meet again on Monday. If I'm not wrong, I think it will still be 10 o'clock. 10:15. Now I need to correct myself. So 10:15. Then I think we are going to look much closer on the multi-object optimizations. It was not like that a few years ago before Matthias and I joined at Uppsala University. But this topic, multi-objective optimization, we have been teaching this in Skövde for I think 15 years, maybe even more. And then the research project with automotive industry even traced back before more than 15 years ago. But it was something pretty new to Uppsala University, if not to the mathematical department, if not to the basic science department, then it must be something very new to industrial engineering. And that's why our purpose is not to give you more mathematical coverage about multi-object optimization, but it's more about how real-life application in production and logistics, they can be much benefit with a multi-object optimization than something you call single objective optimization. The preface here talk about the chapters and they refer to the handbook. So before many of you stream into this lecture, I asked some other students who came earlier, and they mentioned they have gone to chapter 5 or not even start chapter 6. So the information I'm going to give you from today and the next week will start from chapter 7. So there will not be any exercise in chapter 7. Chapter 7 is more about the terminology. So if you have done today and Monday's lecture, then more or less you will already know the information on chapter 7. But the exercise connecting to multi-object optimization and later something more complex relate to something we call selection object, and then relate to some logistic terms, the payoff time as the objective and so on. So they are mainly covered in chapter 8. And then in the tutorial, you have a chapter called chapter 9. And that chapter is more about logistic simulation. So you are looking at some bigger scale optimization problem, simulation model in chapter 9. But in my lecture, for the first two parts, is mainly chapter 8. So after today and Monday, you will have enough basic knowledge in order to go through from chapter 8.2 to 8.4. I need to give you some warning. Is some students find this 8.4 is a little bit frustrated, a little bit more challenging. So, but if you come to 8.4, then it's already come to the most complex optimization that you will do with the basic handbook. And finally, next Thursday, when we meet again on the last 2 hours, then I'm going to tell you, to me, is a quite exciting topic. So how multi-object optimization is connecting to bottleneck analysis. Of course, if you are right down here, of course you know bottleneck would be something important to understand if you are industrial engineers, if you doing something related to production, logistics, supply chain. But exactly how we relay multi-object optimization with bottleneck analysis, that will be something we're going to cover in the last 2 hours. And then you have a lab connecting to that, but that lab is actually not very demanding. There are quite much information there, but not too much that you need to do. You don't need to build a very complex model. Okay, we should talk about something like books. I don't know if you have recognized any of these books in your course literature. The fact is, if you want to complete the lab or complete the course, you don't really need to check the books. I think here would be more like references. So they are not course literature. But if you have heard about Matthias use some of my slides when he started to talk about basic production simulation, and definitely he have gone through some information about factory physics, then I would pretty much recommend you try to find the books in the middle, something called supply chain science. So Wallace Hooper, he is the same author, the same first author of the textbook Factory Physics. But Factory Physics is a pretty thick book, quite typical American textbook. So even though I recommend students to read Factory Physics in so many years, I think there probably were only 2 PhD students who really listened to me. And then one of them became a CEO today. So only those students who really understood the value of factory physics, they really excel. But then if you are saying, oh, you don't have so much time to read the complete book, and then this is not really something related to the whole course, I would highly recommend this supply chain science book because first of all, it's about supply chain. And a lot of those information, they basically just overlap with the factory physics, but in another level. So in factory physics, they're more talking about a factory, but supply chain science, they're more talking about how you apply it to a network of a unit. It can be a network of a production unit, but it can be also a network of a factory, and it makes you a supply chain. So this book is much, much thinner. I have the book somewhere in my room, but if I remember right, I think it's less than 200 pages, around 200 pages, much, much smaller than the factory physics book, which is, I guess it must be 600 or 700 pages. And then for today, I have quite much information relating to matter heuristics. And for those of you who are really interested on the digging deeper into matter heuristic, you think that this is a very interesting topic, I will recommend a textbook from a computer scientist from France. And he has written a book, even though it is more from a computer science approach, but then I think his approach is pretty pedagogical. So even if you're not a computer scientist, I think it's a pretty easy read, and you cover a lot of information, and then both single objective, multi-objective, and very large amount of algorithm will be covered in this book. So they are references, so I do not require you have to read any of those books page to page. But if you're really interested on going deeper into some of the topic, then I will recommend this book. And then when we talk about multi-object optimization, I have a free book here. So on the left one, I was one of the editor, together with a professor in KTH, Li Huiwang, and also a very well-known professor in the field. You will hear his name, Kayamoy Deb. Now I'm pointing at the, let me see if I'm pointing at here, you see the name Kayamoy Deb. And then if you come to here, you also see his name here. And then if you go to the book here, then you will also see Kayamoy Deb. So he is a very well-known professor. Now he is affiliated with Michigan State University. But for those of you who come from India, I don't think it's very difficult for you to recognize this is the Indian name. And he was affiliated with IIT Kanpur for quite many years before he moved back to USA. He got his PhD in USA. And then you will hear about another name later. The name is David Goldberg. And Kayamoy Deb was a student to David Goldberg, which I will talk about later. Okay. Now, quite many things about the information about the books, but again, if you want to dig deeper into any of this topic, I think these are the books I highly recommend. Okay, no matter how much optimization background you have done, I would like to use this figure to go through the terminology, but also some important concept about the flow. Now, whenever you talk about an optimization problem, so you have a real-world problem, and you want to solve this real-world problem. And this real-world problem, in many cases, will relate to something called a decision-making. Why? Because you want to find some solution. And then when you find some solution for some way, no matter you call mathematics, simulation, or now we talk about optimization, you want to solve the problem. But when you find the solution, you still need to make a decision that you will commit. So decision is talking about a time point that you decide that you will commit. I don't know is a good analog to you guys here, but let's say that the marriage is a decision-making process, okay? So to make the commitment, probably you are talking about lifetime, if you are really aiming at the lifetime marriage. But to make the decision that you're going to marry someone, that is a time point that you call decision. So the analog here is that you have a real-world thing you want to relate. And then in our terminology, when we make some abstractions and modeling, and you can make some mathematical modeling. I have one slide about linear programming to refresh your memory if you have done linear programming before. Of course, that type of modeling is already some modeling. But then if you find that you have a more complex line, complex flow, you have some supply chain, and then you have a complex relationship between the ordering and delivering and transportations of your supply chain, then of course, then the modeling will become more demanding, which means that unless you do quite much abstractions, you still can solve it in mathematics. Otherwise, you also consider to use other modeling method like simulations. I will not tell too much about modeling. That was not the purpose of these lectures, but some of you, especially if I don't know any German here, but in Germany, Part1 is some very popular formalism that you can use to make a model about some real thing. Is a mixture of mathematics and also graphical. But if you already know how to use simulation, then of course simulation is one method. Now from your model, then you come to a middle world here. We call optimization model formulations. So you have your model, and sometimes it's just a mathematical functions. You have the evaluations. So this part is done by the model, but there will be some other part we call optimization done by the optimization algorithm. And in mathematical modeling, like linear programming, the functions and also the optimizations part, they are mixed together. So that the model by itself is already including the objective functions. But in many problems, I think the objective functions come only as a small part of your iterative model. So later, when we're looking at the more terms, when we talk about variables and the relationship with functions, that you understand better. So whenever you formulate your problem and then you start to have a model, and in your model, you have the objective functions, then you are closer to an optimization problem. But then there are also something necessary, because you see here, I have another black box here. You see the dashed line there? So an optimization problem must include an objective function or many objective functions, several objective functions. But another thing that is also solid here is that you need to have the decision variable. So this word here, decision, and then we talk about decision making. So decision making and decision variables, of course, they are linked to each other. And you may ask, okay, are there some other variables that you're not going to make decisions? Then the answer would be, of course, because of in a model, in a problem, you have a lot of things that you cannot change. So for those of things that you cannot change, sometimes you call them uncontrollable parameters. Sometimes you call them environmental variable. So in logistics, I can tell you in modeling, there is a one variable, even though when you build a model, you put it as a variable, but normally it's not very easy that you can change it by yourself, no matter in the real world or in the simulation world, is you call demand. So demand is a very interesting environmental variable that is a variable. You can try different things in your model, but in real life, it's more difficult to change. You can connect it to marketing. So if you try to do some campaign in order to sell more, you try to control, try to boost your demand. But in real life, usually it's something that is very difficult to control. So decision variables. And then you see another dashboard here is more dashed, is a constraint. And constraints, they are connecting to decision variables. Now, when you make your optimization formalism, sometimes you already choose your optimization method in here, but sometimes you can find another optimization algorithm. I think I have more information here. Let me see. I think identify the input and output to the model. This is a step that you can connect to decision variable. But then the next step, if you come out of this box from your modeling formalism, then you able to choose some optimization algorithm after you make the model. Now you run the optimization. So in mathematical term, you can get some optimal solutions if you're using linear programming. But then in using other method like the materialistics, then as we already mentioned, this is called the near optimal. And it depends on your method. In some mathematical modeling, you only find one single solution, and that would be optimal if you find it. But in the materialistics and many other methods, you will find a list of solutions. And that means you need to compare those solutions if they are multi-objective, or you still need to ask yourself. Sometimes it's very interesting to ask why we need this decision making. The reason was because of you need to verify that the results that you find actually both satisfies the real world, but also you need to verify whether they are feasible, whether they are correctly formulated, and so on. And that's why verifications and evaluations against some other information, higher level that you didn't include in your model, or you even want to make the evaluation by considering more factors in the real world that you have not considered in your abstraction and modeling. So this loop here is important because of before you really get sure that you want to decide to implement a solution, this loop will continue. And then if you make the decision and then you implement in the real world, then of course this is the real implementation that you find the change in your real life. Now, the information here will be more like a summary. But then some key terms I mentioned, in most cases, optimization problems, they are also decision-making problems. But before we move on, then we need to emphasize that when you can solve a problem by using optimization, it also means that the problem is quantifiable. I talk about marriage, and then in earlier this year, in one of my lecture, I also mentioned that to the students, I was something like joking. If your decision-making problem is to find a boyfriend or girlfriend, then probably that problem is not really quantifiable, even though, of course, in industrial engineering, you almost always can find some quantifiable problem. Why? Because you can always convert the problem into cost or profit and so on. But if your problem is to find a boyfriend or girlfriend, then maybe it's very difficult to quantify, unless you say that you want to find someone that is very rich. That may be quantifiable. But then later, you need to know that the trade-off this term here, they not only talking about trade-off among different solutions, as we will look at the multi-objective. It's also about if your model is a easily to be solved, that means usually the level of details will be pretty low, or you have very high abstractions. So the higher level of details, that means the lower level of abstractions always will give you problem to solve the model. And that's why we need to have something more complicated than linear programming when we want to do simulation-based optimization. The reason was because of in simulation, why you want to use simulation. One advantage is that you can put in a lot of details, a lot of logic, a lot of data into your simulation model. And the more things you put into your model, it will reduce the solvability. So that is always a trade-off between solvability and applicability. That is something we need to know about the problem. So decision-making problem, quantifiable, and then trade-off between solvability and applicability. Now, in many cases, the nature and structure and properties of the model formalism already decide the optimization method which are suitable. Let's say that no matter you have made your decision that you only are able to use a linear programming, then you know the term already tell you that you have to formulate your objective and all constraint to be linear. And then if you find that your problem cannot be formulated into linear objective and linear constraint, then that means a linear programming will not be the right approach. So before you select the optimization model to use, then you already ask yourself, okay, how will you formulate objective, constraint, and so on? So if you decide, or the nature of the problem, decide that they have to be non-linear and even non-continuous, then of course, then you will limit your choice to other things. And then some method like materialistic and simulation-based optimization, they allow the choice of the optimization algorithm to be made later because of those algorithm. The good thing is usually they are, sometimes we say generic, but I think the better term there will be more like the black box is the optimization. They see the model part is like a black box, and then the modeling also see the optimization as another black box. So there is a very clear cutting line between them. But the genericity is also another term. And why? Later, when I talk more about the variable and then how you connect to materialistics, then you will know that it's not all method will be like that. But the materialistic, they only treat the decision variable as a number. They don't really care about which domain. And finally, many optimization methods, they only can find near optimal, and in plain English, we mean the good enough solutions. And then this term sometimes is interesting to discuss deeper. I mentioned about you need to make them decision after you find the solutions. And in both in the literature and also in practical collaboration with the automotive industry, we know that people sometimes, even though they find a solution that is optimal, based on the information they put into the model, yes, they find the optimal solution. But finally, they would make the decision that they want to choose the second choice or even more inferior solution far away from the optimal solution. There are multiple reasons, but a very simple reason was because of you can't have your model that consider all the factors that you need to make the decision. So the model, the optimization can help you, can assist you to make the decision, but then it has no guarantee that it include all the information that is needed. And that's why you always have some other factors to consider. And that is the very last sentence I put here. So a mathematically optimal solutions with respect to the formulated model may not be the best or not even the realistic solution to the real world problem. Now, this will be interesting. Remember, when you go out to the industry and then later even work as industrial managers and so on, okay, then remember sometimes what you learn from today in the school was not something that, oh, you can directly apply and then solve your problem and make you a good career. Many of those things that we teach, that you learn, that you read from book, like optimization, in real life it's very seldom that people can find mathematically optimal or even near optimal, because in real life you have other constraint. For example, you have a very limited time in order to make decisions. But we emphasize that no matter you learn from simulation or optimization, is a learning process, and then it's also iterative. And that means that sometimes you use simulation and optimization not because of you rely on it to replace you, to let you know that what will be the crystal ball that you can see the future. I think sometimes it's more about how you use the model to learn more about your problem, to understand better. And that's why this iterative and learning process has to be emphasized. So I don't think I will spend too much time on this one now, because this more or less take what I mentioned in the figure, but now put into some more mathematical term. So you have the functions, and it has to be maximized and minimized. And then whenever I talk about objective functions, I always like to tell like the story in the Alice in the Wonderland. It's always like that. So when Alice come to injunctions, so she asked the cat, so which way to go, because that was the junctions. And then the cat asked her back, so where do you want to go? And then Alice's answer was, no, I don't know where I want to go. And then the answer of the cat was, then it doesn't really matter. So if you don't know where you want to go in your life, if you don't know what you want to optimize, then to you, this is not an optimization problem. So you don't need to bother. And then optimization problem must be either maximized and minimized. And then you may say that, no, my problem is actually try to be as close as possible to zero. Let's say that that would be a possible objective. And in that case, usually the function you want to find is try to minimize the distance from zero. Okay, so that is the way that you formulate the problem. And then you can always convert a minimization problem to maximization problem by reciprocal or by negative. But if you put the negative function, then you also have some other negative effect, which we will talk about later. Then decision variable representing in a vector. And this is so when you define in fact software, you define the variables as a list of variables. But in an algorithm, normally you cook them into x1, x2, and so on. And then you put this into your algorithm and tell that these are the things you are able to change. And finally, you may have constraint or you may not have constraint. And then constraint means that your vector, now this x is this x here. So when you put into a vector and this talk about your decision variable, will be bounded by functions, and this function is bounded by certain variables. Of course, you may ask, can it be bigger than? But if it's bigger than, then probably you will make your problem to be infinite in your size of problem. So this is very usually when we put constraint, we put the smaller than or equal. And then I will give you an example later. When you make this sign to be equal, it's very simple in mathematical term. But in some algorithm, especially materialistics, if you see your constraint, if you have a problem that you have a constraint that you have an equal sign here, as I try to point here, then for some algorithms, so for some software, then you will have a big trouble. I will also tell you later why you have trouble when we come to materialistics. An optimization problem is linear when all of the functions, now in this case, we have one function, single objective, but then we have multiple constraints. If all of them are linear, but not only about that, you also need to have all variables are continuous. But practically, many of those software package you find in even some algorithm you easily can download from Python. I know that many of you already start to learn Python in other courses, or maybe you already know, especially if you are interested in doing data mining. Nowadays, it's very common to use Python. And then also later in my course, I will teach you something in MATLAB called a MOO. So for those kind of software package, normally all the variables are continuous. Here, you may have problem with many logistics problem. Think about that. The number of cars, number of trucks that you want to put into your supply chain, your transportations. And then in manufacturing, number of workers, number of machines, and they are not continuous because you simply cannot have a 1.235 trucks, 1.2 workers. So even though you can round up the number from what you get from the model, but in real life, in supply chain or in production, we usually have a lot of we call discrete variables or integer variables. So that means this type of problem is not directly give you an answer, which you need to have some round up, which we will see later. But then another interesting thing is I talk about these workers and so on, but there is actually another type of variable, which is called a categorical variable. Categorical variable means that you can put it as a number. But the number actually is not meaning that 1 plus 1 is 2. So 1 and 2, they mean very different thing. And numerically, you cannot put any meaning to relay them 1 to 2 to 3. Let's say that we have something called the dispatching rule. How you use many different rules in your scheduling. that you find in production or supply chain. When you have a list of product in your warehouse, how would you want to make the sequence they come out from your warehouse? So this is a very typical problem in the supply chains. So you can apply many different rules, and those rules you can put the number on them. So number one means very simple, first in, first out. And then the second rule means the last in, first out. So let's take very simple example. So 1 and 2, if you formulate into the problem and say that you want to make decision, they actually don't mean anything. So linear programming cannot directly address integer problem. And then that's why you need to go for something called integer programming. But then another type of problem will be categorical variable. So this is something that good to understand. The variable can be in different type of variables. And then in mathematical form, then of course, we like to relay these objectives. Let's say that the objective can be related to your decision variable. Now, this is something interesting that you have the constant, and then normally you put all those variables together by summations, and then your objective is to minimize. So by formulating into linear programming, you can use something called simplex method or interior point method, and you will find exact optimal, so mathematical guaranteed, if your problem can be formulated into linear. And then they are usually easier to solve because of, we call the problem is convex. So what do we mean by convex? Let's take a very quick example to refresh your memory about linear programming. I don't think I will like read very detailed, so I quickly show you. Now is almost the time that we should have the break, but I can give you all the information. This is a typical, when you do linear programming, this is a classroom problem. You have 2 machines, and then totally available hours per month will be 700 hours. And that means you cannot have the machine time together will be over 700. So this already spell that you are on some constraint already. And then to make this product, you need to have the hours from the machine. So product 1 to 4, each of this product will need the hours from the machine. And then the more you make, your decision variable is to decide the number of units of the product to be produced. And then you have a 4 product. And of course, this looking at the first constraint, you have the hours needed for product 1 if you decide it will be X1, and then hours for product 2, X2 need 7 hours. Then of course, not difficult to see why the constraint here will give you the bound so that you will not exceed the available hours of the machine. The same principle for the second machine. I will not go for details. But now, for the labor, you also have the same constraint, but you have a bit more information about from the labor. Why? Because the labor will give you the cost. Let's assume that the machine will not cost you anything, but the labor will cost you something. So when you use the labor in per hour, then you need to times the dollars per hour. Same thing for another type of unskilled labor. And if you sell the product, you will earn the money. And that's the typical objective functions. You maximize your profit. So looking at this function, practically is talk about the profit because of you have the positive signs is coming from what you earn by selling your product. But then you have the minus sign here, you have the negative part here is the cost. And for this solution coming from simplex method, you find that this is exact the thing I'm talking about. You get the solution, but they are not integer because we use linear programming. You can round up. You can decide that you want to round up or round down. So in this 16 case problem, you want to round up, but then in other case, you want to round down. I don't know, I use this example to simply to stimulate you to think one thing. Now, you get the solutions. The solution cannot apply directly. So you need to round up and round down. So what happens if you round up and round down? What can be the consequence if you round up or round down? you can imagine that if you round down, you earn a bit less. So your profit, of course, will be affected. But the real problem might be, let's say that you round up for this one, then you exceed the first the quota for X1 because we talk about product one, and it might very likely that you already make the solution not feasible because you already exceed this 700 hours as the boundary. So this is some problem that you need to consider when you have the formalism later when you have the optimization. So how it fit back into the real world in this case is not even other factors that you not consider in the information that we give in this slide. It's still the same slide, but still you need to consider what happened. Of course, one practical advice here, maybe you just round down everything. There might be a possible solutions, but then it will give you less money to earn. I think I stop here, and then even I will stop a bit the recording. Any of you want to ask me some questions before we proceed? I think it's good to have a break, but any of you want to ask me something now? I don't notice anyone have written down anything in the chat.